So here is some data, and what I have are 60 months of returns. So 61 months of prices from Yahoo Finance, from which I've calculated 61 months of returns. And I have this for this fund, which is the William Blair Large Cap Growth Fund Classic LCGFX, and this is just a random large cap growth fund that I chose for this exercise. And you can see the returns of this fund in each of the last 60 months. And in the column next to it, I have, the return for IVW. And IVW is the return to an ETF, an exchange traded fund, and we'll talk about what that is later on, that tracks the S&P 500 large growth index. And so this is going to be the returns from actually investing in a benchmark of large growth stocks. And so we can compare this active portfolio, LCGFX, to a passive index investment, IVW. And you can click these links to find out more about these funds and to see where this data came from. So the first thing I need to do is compute the difference between the active and the benchmark in each period for these 60 months. And so I'm going to bring this down and I'm going to compute this. And this is going to give me, once I compute the average of these numbers, here I have the average deviation. And so the way to interpret this number is, and it's tough to sort of see, but on average, the blue line was 20 basis points or 0.2% per month above the orange line. And so I can see that this portfolio actually beat the benchmark. The average deviation was higher. And in sort of a simple way, I can assume that it'll continue to do this going forward. The next thing I need to do, and by the way, we need to do this manually because there is no function for computing this in Excel. So I need to square each of these values. Note that a squared of a percent is not a percent, and so I have these in decimal form. And I'll bring this down, and I'm going to lose my bottom format here, so I'll bring that back. And so now I can compute the sum of these squared deviations, and I think I missed my equal sign, equals the sum of these squared deviations. And now I can take the sum of the squared deviations and I can divide by, and I know there's 60 of them, so I can divide by 59. And now I can compute the square root of the sum of the squared deviations divided by n minus 1, and that's going to give me my tracking error. And so now I have a tracking error of 3.46% and an average deviation of 0.20%. And so what I can do now is compute the information ratio, which is this number, and I get a 0.576%. And what that means is that I only need to go 5% of a deviation, a tracking error, to go from this expected beat of 0.2% to 0. It's telling me how many of the tracking errors I need to go from this average deviation of 0.2 to an average deviation of 0, and I can see it's not very many. This is a very low information ratio. Now, it's very common to annualize this. And so what I'm going to do is I'm going to take this monthly average deviation and I'm going to multiply it by 12. And I'm going to take the monthly tracking error, and this is a little confusing, just like a standard deviation. I can't multiply it by 12, but I can multiply the same way the variance by 12. I can multiply the square of this by 12. So I square it, I multiply it by 12, and then I take the square root. That's the same as multiplying it by 12 to the 0.5. And I get this 11.9. And from this, I can compute the annualized information ratio, and now I get 0.1996 as the annualized information ratio. So what do I do with this number? What do I do with this 0.1196 annualized information ratio? Remember, it's telling me the number of the tracking errors it takes to go from this annualized mean deviation of 2.39%. Remember that this fund is beating the benchmark by 0.2% per month or 2.4% per year, but there's some volatility associated with that. And so the question is, how likely is it going forward to beat this? And I can essentially look at this kind of like a z-score. What I can do is I can compute equals norm.s.dist of this number. And remember, it's negative because I want to look at the distance between 2.39, 0 and 2.39. So the negative of that, comma, true, like that, and I get this 0.42 or 42%. How do I interpret that number? Well, the idea is that the area of the curve to the left of the mean minus 0.1996 standard deviations is 42%. And so the way to think about that is that there is a 42% probability that this fund won't beat the benchmark next year. And how likely is it to beat the benchmark? Well, it's just going to be 1 minus that. There's a 58% chance that the fund will beat the benchmark. And so given that I have an expected beat of 0.2% or 2.39% annually, but a deviation about that expectation of almost 12%, then I can see that I only need to go 0.2 deviations to go from this expectation to 0, and therefore there's a large portion of this probability that I won't actually beat the fund. Sorry, that the fund won't actually beat the benchmark index. And so here's a chart which shows the returns of the two. Here's sort of a bigger version, a better version of those charts. And you can see that there are months in which the blue line, the active portfolio, beats the benchmark by a lot, but there's also months where it loses by a lot. And here's the deviations. And what we're saying is if this were pretty consistent, if this were pretty flat, then I would have a higher probability going forward. But you can see some of these big swing months where it does a lot better or does a lot worse. These are what is lowering the probability, the expectation going forward. Okay, that's the end of the material for indices and benchmark, comparing an active portfolio to a benchmark portfolio. We'll continue on with chapter 10, which is the multivariate regressions and the multi-factor models, looking for multiple priced factors, multiple things that might explain a security's or portfolio's returns and not just the market return.